are a little bit truncated on time. Requisite Math, as I've stated before in Google Classroom and through emails, is something that you will have to complete on your own. Since it's a review, it should not be a new material, but if you need to brush up, I'm providing this video as a walkthrough. These slides are available in our Google Drive folder, so you can access them at any time. You can ignore this. This is from last year announcements. So scientific notation, as an example, 534.3, okay? So any number can be expressed in the form m times 10 to the nth, where m is called the mantissa and n is called the order of magnitude. For writing scientific notation, we do as follows. We start at the decimal point, and we move the decimal point to the left until we are between the first and second digit, okay? In this case, that would be 5 and 3. We count the number of spaces we have moved. Okay, so from right here to between 5 and 3 is 2 spaces, and this represents the order of magnitude. In this case, the order of magnitude is 2. So you use the resulting number 5.343 in this case, and the order of magnitude to write your answer. 534.3 equals 5.343 times 10 to the second. Now let's look at a number that's less than 1, okay? So if I have 0.00023, 6 zeros followed by 2, 3, what we're going to do is we're going to start decimal point and move the decimal point to the right until you're between the first non-zero digit and the second non-zero digit. So in this case, that would be 2 and 3. We're going to count the number of spaces you moved, except this time the order of magnitude will be negative. So 1, 2, 3, 4, 5, 6, 7. The order of magnitude is negative 7. Use the resulting number and order of magnitude to write your answer. So 0.00000023, that's a mouthful, equals 2.3 times 10 to the negative 7th. Multiplication and division, scientific notation. If I want to multiply m times 10 to the 8th times n times 10 to the bth, eighth and bth, that actually sounds kind of funny. You take the mantissas and you multiply them together, so m times n, and then you add the exponents, or you add the order of magnitudes together. So you're going to get 10 times a to a plus b. This relies on exponent algebra, which if you have not been exposed to, and you should have been exposed to it if you are taking this class because it means you've taken Algebra 2, but if you've not been exposed to it, please make sure to brush up on your exponent algebra. Now with division, it follows a similar logic, except now we're going to divide the mantissa, so it should be m divided by m right here. It says multiplied, but it's m divided by n. And then we multiply by 10 to the a minus b. So now when we divide the exponents, that's resulting in the exponents being subtracted. Solving equations in terms of variables. Variables are representative of numbers, thus they can be operated on the same way numbers are: addition, subtraction, multiplication, and division. We proceed by isolating the variable we're interested in. That should be a apostrophe right there. I haven't had time to go back and edit through my slides yet. We're interested in as if we were dealing with a standard equation. So as for example, solve the following equation for y. Y squared x minus 3 divided by z equals 4z. So what we're going to do here, again, we're trying to solve for y. We can treat x and z as numbers, okay? So we can perform the same operations with x and z as we do with regular numbers. So in order to get y squared or y by itself, we're going to start by multiplying both sides by z. And so as a result, we get y squared x minus 3 equals 4z squared. So now what we're going to do is we're going to add 3 to both sides, which is going to give us 4z squared plus 3. So we've ended up with y squared times x equals 4z squared by plus 3. So now we're going to divide by x in order to get as a result, and I got to wait for this little clicker right here to go away. We divide by x to get y squared equals 4z squared plus 3 divided by x, like we see right here. And again, I got to wait for this little clicker to go away. So as a result, we take the square root of both sides, and we're going to get that y equals the square root of 4z squared plus 3 over x, where the square root is also acting on the over x part. Okay? So if you're in this class, physics again is a math-intensive class, you should be familiar with equation solving, so this is a little brushing up on in terms of solving with variables as opposed to just numbers. Unit conversion. If we want to, so we have 3 base units in the standard metric system. We have the kilo, we have the centi, and we have the milli. Okay? So a kilo is 1,000 times a base unit. Okay, so kilometer is 1,000 meters. A centi is 1/100th of a base unit. So for example, 1 centimeter is 1/100th of a meter, which is why we have 100 centimeters in a meter. And then a milli is 1,000th of a base unit. So a millimeter is 1,000th of a meter, and hence we have 1,000 millimeters inside a meter. So for example, if a kilometer is equivalent, a kilometer is equivalent to 1,000 meters. That should be edited there. I'll go back and look at that later on. Again, like I said, I haven't had time to go through and edit my slides yet. So in order to convert between units, say we want to convert 34.6 centimeters to kilometers, we start with the beginning unit and multiply by its conversion to the base unit. So 34.6 centimeters, we convert to the base unit, which is meters in this case. So we're going to have 0.01 meters in a centimeter. Or another way you could write that is that in 1 meter we have 100 centimeters. Both are equivalent. So as a result, we get that 34.6 centimeters is equal to 0.346 meters. So the units on the top and the bottom are going to cancel out, just like numbers, leaving us with a single unit, meters in this case. You're going to repeat this process until you obtain your desired unit. In this case, we multiply by the conversion of meters to kilometers. So 0.346 meters times 1,000 meter times 1 kilometer over 1,000 meters is going to be equal to 0.000346 kilometers, or 3.46 times 10 to the negative fourth kilometers. Again, the meters cancel out, and we use the conversion that in 1 kilometer there are 1,000 meters. And this is the procedure for unit conversion. You don't have to do step-by-step like I've done here. I did step-by-step just to illustrate. What you can do is do it all by at once. So you can do 34.6 centimeters times 0.01 meters per centimeter times 1 kilometer per 1,000 meters in order to get your answer. So you can combine the two prior steps by multiplying the results together in order to get one single step-by-step solution. Okay, and we come back to our check for understanding. This is what I usually would have done with my class at this point on their whiteboards, but we're not in class. So another brief discussion we'll have. Again, my class is very discussion-based and practice-based, but unfortunately we're not very much in class at this point. So for our discussion here, a truck on a road trip across the United States, it starts in Phoenix, reports its location as 30 miles outside Phoenix. We want to know, is this enough information to determine the location of the truck? Well, if we think about things, it's really not. It could be 30 miles northeast, it could be 30 miles south, 30 miles west, so on and so forth. So what we need is an additional direction in order to specify the location of the truck. So this distinguishes what we call a scalar from a vector. So a scalar is a quantity independent of direction, in this case 30 miles outside of Phoenix. A vector is a quantity that has a direction. So as an example, if we want to take this scalar and make it a vector, we'd have to specify an additional direction. We'd say 30 miles northeast of Phoenix. So a scalar is a quantity independent of direction. A vector is a quantity with a direction. We call the quantity part of a vector a magnitude, and then the direction part is, well, just direction. Yeah. Nothing too interesting there. No interesting name for direction. Lo siento. So we're going to combine vectors in a second with trigonometry, so it's worth going over the relationships of trigonometry that we need for this course. So recall that if we have a triangle with a hypotenuse h, a opposite side of length O, and an adjacent side of length A, we can get that sine of theta is equal to opposite over hypotenuse, cosine of theta is equal to adjacent over hypotenuse, and tangent of theta equals opposite over adjacent, also known as the more colloquial name, SOHCAHTOA. So analyzing vectors of trigonometry is what we'll now look at. So a vector can be represented as an arrow. The magnitude is the length of the arrow or the hypotenuse of a triangle. For direction, the convention is we're going to have theta degrees north or south of east or west. So we see right here, here's our conventions that we're talking about. So this is our vector A. The length of the vector, the magnitude or hypotenuse of a triangle represents the quantity, okay? So this would be like 30 miles outside of Phoenix. To get our direction, the direction is specified by the angle between the hypotenuse in the x-axis. So as a result, we say that we're some angle theta degrees north of east in this case, because we're pointing towards the east, and our x component's pointing towards the east, and our y component's pointing towards the north. So we say we're theta degrees north of east. If our arrow is pointing over in this direction, we would say our angle would still be the angle between our hypotenuse and x-axis, but now because our vector would be pointing in the west direction on the x-axis, and in the north direction, the y-axis, we would say that we're theta degrees north of west in this case. So vector conversions, okay? If we're giving magnitude and direction, aka we're given the length and the hypotenuse a, and we're given the angle theta, we can use trigonometry with sine and cosine in order to determine the components x and y of our vector, aka the legs of our right triangle. So we have ax over a equals cosine of theta, hypotenuse adjacent over hypotenuse, and solving for ax gives us a cosine of theta equals ax, what we see right here. And then if we want to solve for ay, we do a similar thing, where now ay is going to be equal to ay equals a times sine of theta, by again solving for sine of theta equals opposite over adjacent. So that's if we're given a magnitude and a direction. So now if we want to go from components to vector, magnitude, and direction, say we're given ax and ay, and we want to determine our vector magnitude and our direction, the magnitude can be found by applying Pythagorean theorem. So our hypotenuse, our magnitude of our vector, is equal to the square root of ax squared plus ay squared. And then our direction can be found by taking note of the fact that if we divide ay by ax, that's going to be opposite divided by adjacent, which is equal to tangent of theta. So our angle theta is going to equal the arctangent of ay over ax. This is stuff you should have covered in Algebra 2 and Geometry before. If not, and this video does not suffice, we'll go over this on the first day that we're back in class, or we can go over it on syllabus day. But if you are in this class, as I've said, you should have seen and been exposed to this stuff before, at least at even an introductory level in Geometry and Algebra 2. So as an example, provide that a vector has the components bx equals 6 and by equals -3, we want to determine its magnitude and direction. So in order to determine the magnitude, again the magnitude is a hypotenuse, we apply Pythagorean's theorem. So the magnitude b is the hypotenuse, it's going to equal the square root of bx squared plus by squared. So we're going to get the square root of 6 squared plus -3 squared, which equals the square root of -45, or 6.71. So the magnitude of our vector is 6.71. Now to find our angle theta, okay, we take the arctangent of by over bx, which is going to be -3 divided by 6, which gives us an angle of -26.5. Please make sure your calculator is in degrees, not radians, okay? So the angle of -26.5 means that we're going to be 26.5 degrees south of the x-axis, okay? If you don't recall from trigonometry, a positive angle corresponds to rotating around the unit circle in the counterclockwise direction, while a negative angle corresponds to rotating in the clockwise direction, starting from the x-axis. So as a result, we're going to be 26.5 degrees south of the x-axis, and then we're going to be pointing east. So our direction is 26.5 degrees south of east. We can see this from the components because bx is equal to 6, which tells us, since it's a positive number, that their x component is going to be pointing towards the east, and then since by is negative, that means our y component is going to be pointing towards the south if we plot the numbers. So that tells us our angle is going to be south of east. We do have a check for understanding here, but we are not going to be able to do that here, so we'll go over, well, not over the solution since I don't have the solution posted on there, but the solutions are posted in the respective Google Drive folder for 0.3. So lastly, we'll go over adding vectors and changes in vectors, okay? So if we wanted to add two vectors A and B, like this right here, okay, what we're going to do is what we call connect tip to tail. We connect the tail of B to tip of A, and then we connect the two resulting vectors, okay? So if I'm adding A and B, the tail of B will get added on to the tip of A. We see that where A ends is where B starts. And then what we do is we connect the space in between, and this gives us the sum of our vectors A and B. To determine the change in a vector V, we connect the vectors by their tails and draw a vector going from the first vector V1 to the second vector V2. So if I have a vector F2 and I have a vector F1 and I want to tell what the change is, I'm going to connect each vector by their tail, and then I'm going to connect the results going from F2 to F1 in this case. Okay? So with adding vectors, tip to tail, and then connect the dots. With change in vectors, we connect the vectors by their tails, and then we connect the dots based on where we want to go. So if we want to determine a change from F2 to F1, we go from F2 to F1. If we want to determine the change from F1 to F2, our vector would now be pointing from F1 to F2. And lastly, we cover mathematical relationships. So we will need to know this for the course. Direct relationship, y is proportional to x. As x increases, so does y. Here's what the graph will look like. Inverse relationship, y is proportional to 1 over x. And this tells us that as x increases, y subsequently decreases, what we see happening right here. As x increases on the x-axis, we can see that our curve decreases on the y-axis. And then lastly, we have the quadratic relationship that y is proportional to x squared. The graph is nonlinear and has a quadratic form, such as this right here. Okay? And these are three relationships you need to be familiar with for AP Physics.